When you look at the night sky, you see thousands of stars with nothing but your eyes, especially far from city lights. But in reality, there are many more stars, too faint for us to see. Every single star you can see is a part of our Milky Way Galaxy, our heavenly home that has captivated human curiosity for ages. The shimmering band of stars, dust, gas, and dark matter that makes up the night sky captures our attention. These elements are all held together by gravity. As we navigate through the cosmos, an intriguing enigma emerges: what is the Milky Way truly like? What makes it up, and where does our solar system exist within it? For centuries, astronomers have been baffled by these fundamental questions, and finding answers has been no easy task. But beyond its luminous beauty lies a tapestry of mysteries waiting to be unraveled. Join us today as we embark on an epic journey around the Milky Way, uncovering its mysteries, wonders, and majesty. You're probably somewhat familiar with our solar system. You likely know it contains 8 planets in addition to the Earth, the Sun, moons, and several other celestial bodies like asteroids and Pluto. However, there's a lot more beyond the solar system that you may not be aware of. From Earth, we can see roughly 6,000 stars without the use of a telescope. Even though that seems like a large number, it represents only a tiny fraction of the total. For every star you can see, there are more than 20 million you cannot. Most stars are either too dim, too far, or obstructed by cosmic dust clouds. While the Milky Way Galaxy contains all these stars, there are other larger galaxies as well, including the Andromeda Galaxy. Every galaxy is a system made up of various stellar remnants, interstellar medium, and star systems. Astronomers believe there are 100 billion galaxies in the cosmos, yet they are not sure. Intergalactic space, which contains thin gas, lies between these galaxies. Given the size of our solar system and the fact that it is only one of many in our galaxy, it's understandable why the universe is thought to be infinite. This helps put into perspective how tiny both Earth and humans are in the big picture. Through the use of radio and X-ray telescopes, scientists have gathered information about the composition of the interstellar medium over the past century. They have shown it is made up of extremely diffuse ionized hydrogen atoms, dust, and cosmic rays scattered throughout thick gas clouds, which are thought to be the birthplace of new stars. But because of the Sun, all 8 planets, and a far-off disk of debris known as the Kuiper Belt, the precise nature just outside our solar system has remained mostly unknown. The Kuiper Belt is located between 30 and 50 astronomical units from the Sun, where 1 astronomical unit is the distance between Earth and the Sun. The heliosphere, a massive protective bubble created by the solar wind, surrounds them all. This bubble acts like an invisible shield, keeping out most dangerous cosmic rays and other material. Without the heliosphere, life would have evolved differently, or maybe not at all. The area where the Sun's magnetic bubble ends and weakens is known as the interstellar space border. The heliosphere, a magnetic bubble, is full of plasma or ionized gas. The solar wind, which pulls magnetic field lines away from the Sun, blows material into the heliosphere with its own magnetic fields and charged particles. The plasma in the interstellar medium exerts an inward push on the heliosphere edge, creating a complex and dynamic structure there. When the solar wind encounters interstellar space, it begins to weaken and slows to approximately 62 miles per hour. Previously, it traveled between 370 and 430 miles per hour. The termination shock is the point at which this happens. The heliosheath is the area in the heliosphere where the solar wind continues to slow down after the termination shock, while the heliopause is the outermost point of the heliosphere. The solar wind stops and gives way to interstellar space at the heliopause, located around 11 billion miles or 18 billion kilometers from the Sun. Since the beginning of human space exploration, only 2 probes have made it to interstellar space, or the area outside of the solar system. After launching in 1977, Voyager 1, the first spacecraft, took more than 30 years to reach the heliopause, a limit that scientists believe marks the beginning of interstellar space. It was an amazing accomplishment, sending back vital information via a medium unaffected by the Sun. As we exit the solar system, we will reach Alpha Centauri, the closest star system to Earth, located about 4.37 light-years away in the constellation Centaurus. Alpha Centauri is a triple star system consisting of 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri AB is a binary star system made up of Alpha Centauri A and B, which are Sun-like stars classified as Class G and K, respectively. These 2 main stars have an apparent magnitude of -0.27, making them appear to be a single star to the unaided eye. Only Sirius and Canopus are brighter, making it the brightest star in the constellation and the 3rd brightest in the night sky. Alpha Centauri B is smaller and cooler than Alpha Centauri A, with 0.9 solar mass and less than 0.5 solar luminosity, while Alpha Centauri A has 1.5 times the luminosity and 1.1 times the mass of the Sun. The two have a 79-year orbital period around a shared center. The distance between A and B fluctuates from 35.6 astronomical units, roughly the distance between Pluto and the Sun, to $11.20, roughly the distance between Saturn and the Sun, due to the eccentricity of their elliptical orbit. I in the Alpha Centauri system, Proxima Centauri is the star nearest to the Sun, located approximately 4.2 light-years from Earth. Robert Innes, a Scottish astronomer, discovered the star in 1915. Proxima Centauri is a red dwarf star, which is the most common kind of star. It is roughly 7 times smaller than the Sun and a little more than half as hot at 3,100 Kelvin, while our Sun is 5,772 Kelvin. This little star is just 50% larger than Jupiter. Red dwarf stars have long lives because they consume hydrogen fuel very efficiently. Proxima Centauri is expected to remain in its current state for more than 4 trillion years. Although the Alpha Centauri system can be seen in the constellation Centaurus, Proxima Centauri is usually not visible to the human eye. Proxima Centauri orbits the other 2 stars in the system, Alpha Centauri A and B. It takes 550,000 years to complete an orbit of A and B. With an apparent visual magnitude of 11, Proxima Centauri is the dimmest of the 3 stars. This star emits light at a slower rate than the Sun, with a luminosity of 0.17% that of the Sun. However, Proxima Centauri is categorized as a flare star, prone to massive solar flares, with its brightness varying by more than 1 magnitude in minutes. These flares occur multiple times a day and can be powerful enough to make Proxima Centauri visible to the human eye. The greatest solar flare ever observed in the Milky Way Galaxy was released by Proxima Centauri in 2019, glowing 14,000 times brighter in ultraviolet wavelengths than normal. Even though Proxima Centauri will live longer than the Sun, it will eventually meet the same fate. Proxima Centauri will end up as a burning white dwarf star because it does not have the mass to turn into a neutron star or a black hole when its hydrogen supply runs out. As of 2022, astronomers have detected 3 planets orbiting Proxima Centauri, Proxima b, c, and d. These are the closest planets outside the solar system. Red dwarf stars are small and cool, so planets can circle quite close to them and still be classified as being in the habitable zone, the range of distance from a star where a planet's water, if any, could be liquid and potentially support life. Proxima Centauri b, discovered in 2016, is estimated to contain about 177% more mass than Earth, making it likely a rocky planet. Despite being far closer to its star than Earth is to the Sun, Proxima Centauri b is still within Proxima Centauri's habitable zone. It orbits Proxima Centauri every 11 Earth days at a distance of about 0.049 Australian dollars, over 20 times closer to Proxima Centauri than Earth is to the Sun. Proxima Centauri b is likely tidally locked like our Moon, with one side always facing its star. Given that it is far closer to its star than Earth, it is possible that liquid water exists on the opposite side. However, its habitability is uncertain due to the extreme radiation flares from its host star. Proxima Centauri b feels the gravitational pull of its star much more strongly than we feel the tidal effect of our Sun here on Earth. The Moon exerts more tidal force than the Sun also because it's so much closer. Tides don't just pull on the ocean, they can also move air. It's possible that the tidal pull on the atmosphere of Proxima Centauri b is up to 500 times stronger than that of Earth's atmosphere. Proxima Centauri b is likely close to the maximum tidal force a planet can withstand and still retain a solid surface. However, Proxima Centauri b's climate and weather are mostly unaffected by its extremely high tides. Situated just outside of the habitable zone at around 1.5 astronomical units from the red dwarf is the mini-nephew Proxima Centauri c, which is around 7 times the size of Earth and orbits its star once every 1,900 Earth days. Initially thought to have been discovered in 2019, this super-Earth planet appears to shine much brighter than expected for its size, indicating that it may be shrouded in dust clouds or circled by a ring system. Astronomers estimate the planet's temperature to be extremely cold, probably close to -233 degrees Celsius, making it uninhabitable due to its distance from its star and large mass. The gravitational pull of Proxima Centauri c caused its parent star's velocity to wobble, leading to the star's initial detection in 2019. In 2020, pictures from the Hubble Space Telescope from 1995 were used to confirm Proxima Centauri c's existence, making it one of the rare exoplanets with visual confirmation that a third planet was discovered in 2022 around Proxima Centauri, known as Proxima Centauri d. It orbits its star at a distance of roughly 3% of Earth's distance from the Sun and contains about 25% of Earth's mass. Every 5 Earth days, Proxima Centauri d completes one orbit around its star. Due to its relative proximity, it is among the lightest exoplanets that scientists have yet observed. Furthermore, in 2021, scientists detected what may be the first indications of an exoplanet circling Alpha Centauri A, also known as Rigil Kentaurus, in the star's habitable zone. Called Candidate C1, it is estimated to have a mass between half of Saturn and Neptune and orbits Alpha Centauri A at a distance of roughly $1.1 Australian. Using direct thermal imaging, C1 was found with an elongation of around 0.1 arcseconds. It appears to be as bright as a giant planet, consistent with the orbital motion of a planet in a 70-year orbit. The discovery of this exoplanet is intriguing, given that it is situated in the habitable zone of Alpha Centauri A and may be a mini-Neptune or super-Earth. We are almost certain that planets similar to Earth exist in Alpha Centauri, but the main question is, could humans ever actually live there? The most challenging obstacle in our quest to set up a new home in the Alpha Centauri system would undoubtedly be traveling the huge distance to reach these 3 stars. Even though Alpha Centauri is the nearest star system to Earth, it is still more than 4 light-years away. That comes to roughly 23.5 trillion miles or 37.8 trillion kilometers. We would need a far faster spacecraft or another means of transportation to cover such a great distance. NASA claims that the Space Shuttle Discovery, which was discontinued in 2011, had a top speed of about 17,500 miles per hour. Reaching Alpha Centauri would take more than 148,000 years even at this steady speed. NASA estimates that even when the Orion spacecraft, the crew capsule linked to the Artemis program, is prepared to carry people, its maximum velocity will be approximately 20,000 miles per hour. This won't significantly cut down the travel time to Proxima Centauri, even if these vehicles were designed to journey out of the solar system rather than just making relatively short trips to the Moon or Mars. As we have already discussed, the only spacecraft to make it out of the solar system thus far are Voyager 1 and 2. Even at their top speed of over 35,000 miles per hour, it will take them nearly 40,000 years to travel 2 light-years to reach the indistinct boundary between Proxima Centauri and our solar system. That implies it might take these spacecraft more than 880,000 years to reach close to the star. After all, it takes light more than 4 years to reach Alpha Centauri. A spacecraft needs to be extremely tiny and robotic to reach a distant star in a reasonable amount of time, like within a generation. Furthermore, it still needs an incredibly strong energy boost to get up to speed. That is the basic concept behind the breakthrough Starshot project. By creating a light sail-equipped nanocraft called Starship, which would be sent into Earth orbit, the mothership would release the tiny probes one at a time. These probes would then ride the beams of a colossal ground-based laser array. The main challenge, though, is the Earth's atmosphere, which distorts laser and incoming light and makes it challenging to apply the force required to move a spacecraft forward. Much more potent lasers on the ground would be able to keep a close focus on the space mission, thanks to small lasers mounted on satellites that would evaluate atmospheric impacts in real time. To send out the vessel at any given time, the required lasers need an astounding 100 gigawatts of power, equal to the total US electricity usage. But the lasers only need to operate for 10 minutes at full power. They plan to employ 100 million lasers to distribute the electricity across an area of 1 square kilometer. The Starshot team is determined to push the boundaries of space exploration. When the lasers are switched off, the object racing through space will be traveling at a stunning 20% of the speed of light, more than 130 million miles per hour or 216 million kilometers per hour. With a diameter of little over 10 meters, this spacecraft could reach Alpha Centauri in about 22 years. However, it might be significantly slowed down by the Sun's gravitational pull and interstellar debris. It will take 4 more years for the spacecraft signals to reach Earth, even if they make it to Alpha Centauri. Alpha Centauri is moving toward Earth, but very slowly and doesn't pose an immediate cause for concern. The distance between Alpha Centauri and Earth as of 2024 is approximately 3.26 light-years. It will be at its closest in 29,700 AD, when it will be approximately 3 light-years away. Over the course of a human lifetime, the slow change in distance will have no noticeable impact on Earth or the solar system. Space is a remarkable place, and we're learning new things about it every day. Leaving Alpha Centauri behind, we travel on to Barnard Star, the second nearest star to the Sun, at a distance of 5.95 light-years. It is named after Edward Emerson Barnard, the American astronomer who made the discovery in 1916. With an estimated age of 11 to 12 billion years, or roughly twice that of the Sun, Barnard Star is an old star and most likely a thick disk member of the Milky Way. Red dwarfs that are young or middle-aged often spin fast enough to produce powerful magnetic fields, which can result in flares that quickly double a star's brightness. However, Barnard Star is too old to show this kind of behavior. On July 17, 1998, Diane Paulson and her colleagues at NASA's Goddard Space Flight Center revealed that a flare similar to this one had been released by Barnard Star. At the time, the star's spectra were being obtained using the 2.7-meter telescope at McDonald Observatory by William Cochran of the University of Texas at Austin. His hope had been to find alterations that would point to the existence of planets in orbit. Instead, he saw emission lines in the spectrum, which showed that the star might be flaring. 4 years later, Cochran's team's investigation revealed that the star's hot blue flare was similar to those from younger red dwarfs, even though it was quite old. The temperature of the flare was at least 8,000 Kelvin, more than twice as hot as the 3,100 Kelvin temperature of the star. As Barnard Star gets closer to us, its distance from us is decreasing by 0.036 light-years every century at an incredibly fast speed of 108 kilometers per second, or 67 miles per second. Its closest approach to the Sun will be at a distance of just 3.85 light-years by 11,800 AD. In terms of its proper motion, Barnard Star is also the fastest moving star in Earth's skies. Another feature that makes Barnard Star unique is its largest proper motion of any star, approximately 10.4 arcseconds per year, equivalent to a lunar diameter every 180 years. Because of this and its relative closeness, it is an ideal target for exoplanet searches, as any systematic variations in its motion across the sky brought on by planets in orbit would be more noticeable. Finally, a planet was found around Barnard Star in 2018. The planet orbits the star at a distance of roughly 60 million kilometers, or 37 million miles, on a 233-day orbit, with a mass at least 3.2 times that of Earth. The planet is not in the habitable zone due to the star's low brightness, and any water on its surface would probably be frozen. As we go farther away, around 8.6 light-years near the constellation of Orion, we will find Sirius, also known as the dog star or Sirius A, the brightest star in Earth's night sky. With a mass twice that of the Sun, Sirius has a diameter of 1.5 million miles, or 2.4 million kilometers. The star Sirius would outshine our Sun by a factor of more than 20 if it were positioned next to it. Within the Canis Major constellation, Sirius is a binary star. The star's name comes from the Greek word siros, which means glowing or scorching. With a surface temperature of almost 18,000 degrees Fahrenheit, Sirius has a bluish tint and is 25 times brighter than the Sun. It is clearly visible in the winter night sky of the northern hemisphere. The ancients were familiar with Sirius due to its extreme brightness. Nevertheless, astronomers were taken aback when Sirius B, companion star, was discovered in 1862. While Sirius A is visible to the naked eye, Sirius B is 10,000 times fainter. Thanks to data from the Hubble Space Telescope, astronomers were finally able to estimate the mass of this faint object in 2005, despite the fact that it is extremely difficult to observe from Earth. Within 20 light-years of the Sun are around 131 objects, including stars, brown dwarfs, and sub-brown dwarfs. Only 22 stars are bright enough to be seen without a telescope, meaning their visible light must be at least 6.5 apparent magnitude, the lowest brightness that can be seen with the naked eye from Earth. The known 131 objects abound in 99 stellar systems. Out of these, 103 are main sequence stars, consisting of 23 typical stars with a higher mass and 80 red dwarfs. In addition, scientists have discovered 21 brown dwarfs, one sub-brown dwarf Y0855-0714, which is possibly a rogue planet, and 6 white dwarfs. White dwarfs are stars that have used up all of their fusible hydrogen. A red dwarf candidate known as Scholz's star and a companion brown dwarf passed near the edge of the Oort cloud around 70,000 years ago. At this moment, it is approximately 22 light-years away from the Sun and has likely triggered a comet storm that will take over 1 million years to reach the inner solar system. The Kuiper Belt object's orbits were impacted by its passage. Some other stars, such as the G-type star HD 7977, have also been researched. It had its close pass around 2.8 million years ago and is currently located about 247 light-years from Earth. Of course, past interactions aren't the only thing to consider. There will be more stars in the future. In the next 15 million years, 694 stars are predicted to approach the solar system at a distance of less than 516 light-years. Based on data from the Gaia telescope's second data release, 26 of them are likely to arrive within 3.3 light-years, and 7 more within 6 light-years. Due to the sheer number of stars that must be surveyed, this number is probably much higher. For example, a star that was approaching the solar system 10 million years ago would be 600 to 6,000 light-years away from the Sun today, whereas millions of stars are now closer to the Sun. Gliese 710, a star, is among the most well-known instances of a close future passage. It is an orange star around 60% the size of the Sun, located in the Serpens constellation. This star is heading in our direction at a speed of 50,499 km per hour, or almost 32,000 miles per hour. In 1.29 million years, it will pass the Sun at a distance of around 10,520 Australian dollars, which is over 100 times the distance to Pluto, which orbits the Sun at an average of 39 Australian dollars and 50 cents. However, it still has the potential to disrupt the solar system. If humans are still around on Earth at that point, we don't have to worry about any disruptions to our orbit. If Gliese 710 has any effect at all, it might only have an impact on the outer solar system. It shouldn't have any impact on anything inside 40 astronomical units, but still, it could possibly cause disruptions to the Oort cloud because it has a very high probability of going through it. For millions of years, comet showers would result from that heading toward the Sun. This might lead to roughly 10 comets visible to the unaided eye every year. Searches for stars that are close to the Sun could not only be an opportunity of finding ancient comets but also of predicting an intriguing future for observers on Earth millions or even thousands of years from now. The local interstellar cloud, which is around 30 light-years large, is where the solar system and the other stars and dwarfs are now moving within or close to it. The local interstellar cloud is in turn contained inside the local bubble, a cavity in the interstellar medium about 1,000 light-years across with an odd peanut shape. Our Sun was far away when the bubble first formed 14 million years ago, but about 5 million years ago, the Sun's path made its way into the bubble. Interestingly, stars formed on the surface of the bubble but not inside it. There are 7 star-forming regions around this bubble. Because of this local bubble, life has become possible on Earth today. As we go farther away, we will reach the Orion constellation, around 1,344 light-years from Earth. 1 light-year is the distance light travels in a single year, about 6 trillion miles, or 10 trillion kilometers. The Orion constellation is one of the 88 modern constellations and is named after the hunter in Greek mythology. It contains over 60 stars, including Betelgeuse, a red supergiant star located around 650 light-years away. This is one of the largest known stars with a diameter of about 767 million miles, or 1.2 billion kilometers. It's about 700 times the size of the Sun and has a mass between 10 and 20 times that of the Sun. Because Betelgeuse may have less than 300 years of fuel left in its core, there has been continuous discussion throughout the world on whether or not it will explode. The star's core will collapse into a black hole as it burns through those final drops, blasting out the star's outer layers at speeds of up to 25,000 miles per second, or 40,000 kilometers per second. Astronomers refer to this blazing demise as a supernova explosion, and in Betelgeuse's case, it will be a breathtaking sight for observers on Earth. Those layers of gas and dust will shine in our sky for several weeks, comparable in brightness to the full moon. Because the star is only 650 light-years away from Earth, the issue is that most astronomers do not think Betelgeuse is quite ready for a big explosion just yet. They normally expect it will blow up in the next 100,000 years, or soon on a cosmic time frame, not a human one. The other famous stars in this constellation are in the line of Orion's belt, consisting of 3 stars located around the middle of the constellation Orion. These are Alnitak, Alnilam, and Mintaka from east to west. The belt is perhaps the most recognizable feature of Orion because it is visible all around the world. These 3 supergiant stars are separately thousands or tens of thousands of times brighter and several times more massive than the Sun. Despite these stars appearing close to one another in the sky, they are actually light-years apart. Orion's belt is mainly used by astronomers as a celestial landmark when searching for M42, also known as the Orion Nebula. M42 is located below the belt and is one of the most visible Messier objects for beginner astronomers, as it is easy to locate and view with a telescope or pair of binoculars. Looking at it is like looking into a celestial nursery where new stars are born. One of the largest gas and dust clouds in our Milky Way Galaxy is the Orion Nebula. It is approximately 2 million years old and located about 1,300 light-years away from Earth. Because the magnificent nebula has an apparent brightness of +4, it is even visible with the human eye. On the astronomical magnitude scale, +6 is the faintest object that, in the best lighting conditions, is visible to the human eye. This massive nebula, which has a diameter of between 30 and 40 light-years, could be giving birth to 1,000 stars. Within the nebula is a young open star cluster whose stars are still only loosely connected by gravity after having formed together in the gas cloud. It is sometimes called the Orion Nebula Star Cluster. In 2012, an international group of astronomers suggested that this cluster in the Orion Nebula might have a black hole at its heart. Through small telescopes, you can see the 4 brightest stars in the Orion Nebula, known as the trapezium. The Orion Nebula is illuminated by the light of the young, hot trapezium stars. In terms of star lives, these stars are young, having only the age of approximately 1 million years. An infrared picture of the Orion Nebula was taken by the James Webb Space Telescope last year. It shows an explosion of dust, stars, and clouds in red, purple, and blue against a background of dark space. Additionally, 540 planetary mass objects with masses ranging from 0.6 Jupiter masses to Jupiter itself have been discovered by James Webb within the nebula. Among these planetary mass objects, the most fascinating are the Jupiter mass binary objects, which aren't separate objects orbiting in space by themselves. Our Milky Way Galaxy is a spiral galaxy. A spiral galaxy looks like a flat rotating disk with a bulge in the center and spiral arms that extend outward from the bulge. While there are many minor arms and just 2 major arms in our spiral galaxy, astronomers used to believe there were 4 major arms. Scientists have found that just 2 arms wrapping off the ends of a central bar of stars dominate the Milky Way's beautiful spiral structure. These discoveries were made possible by NASA's Spitzer Space Telescope using infrared imagery. The 2 major arms of the galaxy, Scutum Centaurus and Perseus, are visible at the tips of a thick central bar, while Norma and Sagittarius, the 2 now demoted minor arms, are situated in between the major arms and are less distinct. Although the minor arms are mainly made up of gas and areas where stars are forming, the major arms have the largest densities of both young and old stars. Large telescopes are used by radio astronomers to study the motions of those hydrogen clouds that trace the arms. With a pitch angle of around 9 degrees, the Perseus arm has a spiral extension and measures over 60,000 light-years in length and 1,000 light-years in width, housing the well-known Crab Nebula in addition to double clusters. On the other hand, the Scutum Centaurus arm is around 55,000 light-years in length and 1,000 light-years in width. Our solar system lies between 2 prominent spiral arms, the Perseus arm and the Scutum Centaurus arm. However, we are not completely free-floating in empty space. We are situated on the edge of the Orion Cygnus arm, sometimes referred to as the Orion arm or local arm, which is a small spiral arm. This spiral arm spans about 10,000 light-years in length and 3,500 light-years in diameter. However, a 2016 analysis indicates that its length may exceed 20,000 light-years. The Orion arm is named after the Orion constellation. The solar system is located in the local bubble on the inner edge inside the Orion arm. It is located at 26,000 light-years from the galactic center, halfway down the length of the Orion arm. You might be surprised to hear that the Sun takes 250 million years to complete one rotation around the Milky Way. This is referred to as a cosmic year or galactic year. Thus, during its lifetime, the Sun is estimated to have completed only 18 to 20 orbits. Since the beginning of mankind, the solar system orbits the Milky Way at a speed of about 220 kilometers per second, or 0.73% of the speed of light. The solar system takes around 1,400 years to travel 1 light-year at this speed, or 8 days to travel 1 astronomical unit. Following the ecliptic, the solar system is traveling toward the zodiacal constellation Scorpius. The last time the solar system was in this position in the Milky Way, there were still dinosaurs on Earth. Who knows when it will happen again? Humanity might be extinct, or it might have evolved into something else entirely. Our place in the galaxy is important because it seems that galaxies have habitable zones just like planetary systems. Many of the Milky Way's suns orbit the galaxy along paths that take them through the deadly spiral arms. An astounding 95% of them may not be able to support habitable planets because the radiation from the crowded stars is deadly for any star that goes through one of these stellar swarms. In order to maintain its alignment with the galaxy's rotation, our solar system orbits sufficiently far from the galactic center to stay in the calmer region between the spiral arms. Within a large and intricate galaxy, the Earth and its planetary siblings are well situated in a quiet, resource-rich region. As we go closer to the center of our Milky Way galaxy, located roughly 9,500 light-years away from Earth in the Scutum constellation, we reach Uy Scuti, considered one of the largest known stars. With a radius of 1.18 billion kilometers, which is 1,700 times larger than the Sun's radius. This hypergiant star has a diameter equivalent to 8 times the distance between Earth and the Sun, or 150 million kilometers, or 93 million miles. Because of this immense size, its outer surface would reach well beyond Jupiter's orbit, which is around 5 times farther from the Sun than Earth. The gas nebula ejected from the star stretches 400 times the distance between Earth and the Sun, far beyond Pluto's orbit. To put it in perspective, more than 1 million Earths could fit inside the Sun, but some 5 billion suns could fit inside a sphere the size of Uy Scuti. Not surprisingly, Uy Scuti is classified as a hypergiant star, the classification that comes after supergiant and regular giant. Although it may be the largest due to its size, it is not the heaviest or most massive star. The term mass in massive refers to the amount of matter in the star. The heaviest star is our 136A1, which weighs in at about 300 times the mass of the Sun but only about 40 times the radius of the Sun. On the other hand, Uy Scuti has a size significantly larger than the Sun, although having only half a mass between 7 and 10 times that of the Sun. Similarly, being so massive doesn't mean that Uy Scuti is that hot either. In fact, its surface is almost half as hot as our Sun's. Another thing that makes Uy Scuti particularly interesting is that it's a variable star. Over time, variations in luminosity can be seen as a result of the material's continuous fluctuation at and near the surface due to the unstable battle between the forces of gravity and fusion. These stars are of special interest to astronomers because they can shed light on the inner workings of stars. Although Uy Scuti, like many other stars, is thought to be capable of supporting a planetary system, it's possible that the innermost exoplanets have already been swallowed by the host star's expansion. Furthermore, Uy Scuti is so faint that it is improbable that we will ever be able to witness those exoplanets directly. As we go to the center of our Milky Way Galaxy, around 26,000 light-years away, we encounter a celestial enigma, Sagittarius A star. This supermassive black hole is an incredible cosmic monster that is beyond understanding. Sagittarius A** is no ordinary black hole. Its estimated mass is a staggering 4.3 million times that of our Sun. Imagine compressing millions of suns into a single point, a gravitational singularity where space and time warp beyond recognition. This massive monster is located at the heart of the Milky Way, our spiral galaxy. A black hole is a region of space so densely populated with mass that nothing can escape from it, not even light. A black hole is invisible to us, but telescopes can see the material surrounding it. Black holes surrounding matter, which can consist of gas and dust, warms up and releases detectable radiation. In some cases, telescopes can observe the gravitational influence of a black hole on the motions of nearby individual stars. Observing it directly is a formidable challenge. Sagittarius A** is obscured by a dense layer of dust that prevents optical observations. However, astronomers have developed smart strategies to break through this cosmic curtain. The Event Horizon Telescope, EHT, a network of radio telescopes spanning the planet, made history in April 2019 when it successfully obtained the second-ever image of a black hole. This discovery comes after the EHT collaboration released the first picture of M87, the black hole at the center of the farther-off Messier 87 galaxy, in 2019. Sagittarius A** was visible in the photograph as a dim outline against the brilliant background. This turbulent region, known as the accretion disk, feeds matter to the hungry black hole, causing occasional X-ray flashes. Despite Sagittarius A** being less massive and more than 1,000 times smaller than M87, the two black holes look remarkably similar. Its surrounding gas disk, which stretches out over a distance of 5 to 30 light-years, can reach temperatures of up to 18 million degrees F, 10 million degrees C. Not only is the supermassive black hole at the center of our galaxy spinning, but it's doing so at nearly maximum speed, consuming everything in its path. Physicists use NASA's Chandra X-ray Observatory to study the X-rays and radio waves coming from material outflows in order to measure the rotating speed of the supermassive black hole in the Milky Way. A black hole's spin speed is represented by the letter A, and ranges from 0 to 1, where 1 is the maximum rotational speed for a specific black hole and represents a significant portion of the speed of light. Physicists discovered that Sagittarius A** rotates at a speed of 0.84 to 0.96, which is near the upper limit determined by the width of a black hole. The spin of a black hole differs from that of other celestial bodies. Black holes are truly regions of spacetime defined by an outer non-physical boundary termed the event horizon, beyond which no light can escape, unlike planets, stars, and asteroids, which are solid things with physical surfaces. This implies that as black holes spin, they literally distort spacetime itself, dragging anything inside the ergosphere with them. This phenomenon, known as frame dragging or the lens-stirring effect, implies that knowledge of a black hole's spin is necessary to comprehend how space acts around it. Additionally, the frame dragging around black holes produces strange visual effects. The path of light gets twisted or curved as it approaches a revolving black hole due to spacetime's rotation. This causes a process known as gravitational lensing, in which the rotating black hole's gravitational pull bends the path of light. Frame dragging effects can result in the production of light rings and even the shadow of a black hole. The theoretical top speed of a black hole is determined by how it feeds on matter and thus how it grows. As matter falls into a black hole, it increases the black hole's spin, but there's a limit to how much angular momentum it can possess. The black hole's mass is another factor. The gravitational attraction of more massive black holes is stronger, making it harder to spin them up. This could explain why the rapidly feeding supermassive black hole at the center of Galaxy M87, the first black hole ever captured on camera, is spinning at between 0.89 and 0.91 despite having the mass of 6.5 billion suns. While Sagittarius A**, with its mass equivalent to about 4.5 million suns, has a spin speed between 0.84 and 0.96. But soon something strange happened while researching this black hole. Some scientists believe that Sagittarius A** may not be a black hole after all. Instead, it could be an immense concentration of dark matter. Imagine a dark pool of invisible matter forming the basic structure of our galaxy. Sagittarius A** has never been directly confirmed despite being widely believed to be a black hole. To put it simply, it is an extremely bright radio emitter located at the Milky Way's galactic core. The astronomy community encountered a challenging problem. G2, a gas cloud, had moved a bit too close to Sagittarius A*. The G2 gas cloud just kept drifting without undergoing any notable changes, despite the fact that the supermassive black hole should have pulled it and destroyed it. Observing the interaction between Sagittarius A** and the G2 gas cloud revealed that G2 was not an ordinary gas cloud. As seen by the lack of effect, they explained that at least two components had to be present to allow the cloud to pass through that close to the black hole without being devoured. One is an extended cold and low-mass gas cloud, and the other is a very compact segment like a dusty object that dominated the detected emission from G2 as it passed by. Astronomers, however, may be more concerned with the possibility that Sagittarius A** is not actually a black hole. First, scientists created a simulation of our galaxy because they were intrigued by the idea that the Milky Way's center might actually be a mass of dark matter. Researchers found that despite the galactic center's replacement, the Milky Way Galaxy still exists and operates basically in the same manner. Throughout the simulations, the behavior of the rotating curve in the Milky Way's outer halo was identical to that of nearby S-stars, or those connected to the radio source Sagittarius A*. Taking their inquiries a step further, they proposed that darkos, a family of particles related to fermions, may comprise the mass at the center of the Milky Way. Apart from its extreme features, such as devouring everything around it, darkos would have the same properties as a black hole if they clumped together into a huge mass. Sagittarius A** is mostly dormant and only occasionally absorbs gas or dust, but nonetheless has an estimated mass millions of times that of our Sun. Although there are still a lot of unanswered questions concerning the supermassive black hole, future observations from the Event Horizon Telescope should shed light on these riddles. Stellar mass and intermediate mass black holes form when massive stars cease nuclear fusion and can no longer support themselves against complete gravitational collapse. The mechanism that forms supermassive black holes like Sagittarius A** is unclear because there are no stars large enough to directly collapse into a black hole of this size. There are two possible explanations: either smaller black holes merge in order to form larger black holes, or smaller black holes grow enormously large by consuming gas and dust from their surroundings. Sagittarius A** remains an astronomical marvel, a cosmic mystery at the heart of the Milky Way. As our understanding deepens, we continue to unravel our galaxy's secrets. In 1970, American astronomer Harlow Shapley provided the first reliable measurement of the galaxy's size. He determined the size by first determining the globular cluster's spatial distribution. As had been previously believed, Shapley discovered that the galaxy is enormous, with the Sun closer to its periphery than its center, rather than a relatively compact system. Assuming that the globular clusters surround the galaxy, he calculated that the galaxy has a diameter of roughly 100,000 light-years, or 600,000 trillion miles. The Sun is located approximately 30,000 light-years from the galaxy's center. His values have held up remarkably well over the years. The Milky Way's stellar disk is roughly the size predicted by Shapley's model. Dark matter, or invisible matter, may fill an even larger volume than expected, while neutral hydrogen is somewhat more widely distributed. According to recent calculations, a dark matter area that includes a few visible stars might have a diameter of about 2 million light-years. In addition to having multiple satellite galaxies, the Milky Way is a member of the Local Group of Galaxies, which is a subcluster of the Virgo supercluster, which is itself a component of the Laniakea supercluster. There are at least 100 to 400 billion stars in our galaxy and at least that number of planets. The Milky Way and everything else in space are in motion. The radiation from the Big Bang, known as the cosmic microwave background, is used as a reference point for calculating the speed of objects in space. The Milky Way Galaxy is thought to be traveling at a speed of roughly 600 kilometers per second, or 372 miles per second, inside the Local Group of Galaxies. Since the oldest stars in the Milky Way are almost as old as the universe, they most likely formed shortly after the Big Bang's dark ages. The galactic nucleus is the site of a wide range of activity, apparently powered by the black hole. The region emits X-rays and infrared light, and it is possible to see fast-moving gas clouds there. Data clearly show that matter, including some gas from the Z direction, which is perpendicular to the galactic plane, is being drawn into the black hole from outside the nuclear zone. As the gas nears the black hole, the central object's strong gravitational force squeezes the gas into a rapidly rotating disk, which extends outward about 5 to 30 light-years from the black hole. Surrounding the nucleus is an extended bulge of stars that is nearly spherical in shape and consists primarily of population II stars, though they are comparatively rich in heavy elements. A star's metallicity, or the amount of elements heavier than helium in its composition, divides stars into three primary population groups. Population III are the oldest, and population I stars are the youngest, like our Sun. The disk portion of the galaxy contains the population I stars, whose ages range from 0 to 10 billion years. The spiral arms include the younger ones. The orbits of population I stars are well organized with roughly circular paths in the galactic disk's midplane. Young star clusters made of population I stars are called open clusters because the stars are loosely bound together, in contrast to the old concentrated globular clusters. Compared to population II stars, population I stars have a higher abundance of elements heavier than helium. Astronomers frequently refer to elements heavier than helium as metals. The oldest population I stars have somewhat eccentric orbits that can carry them up to 3,000 light-years from the disk plane and have a metal abundance 0.1 times that of the Sun. The population II stars inhabit the spheroidal component, the stellar halo, and bulge. They have masses of less than or equal to 0.8 solar masses because they are old, with ages ranging from 10 to 13 billion years. Their orbits are much more randomly oriented than the population 1 orbits and are highly elliptical. As a unit, the spheroidal component has little overall rotation. Population 2 stars make up globular clusters. Globular clusters were used to find the center of the galaxy because they swarm around the center like bees around a hive. On the other hand, population 3 stars are those that have not been directly observed. They are believed to have virtually no heavy elements at all. These stars are thought to be the first ones that formed in the primordial universe shortly after the Big Bang. They were extremely massive and hot, burning their fuel very rapidly and turning hydrogen and helium into heavier elements. When they die, they explode as supernovae, scattering some of these elements into the surrounding space. These stars probably created the first heavy elements that became part of later stars and played a key role in the formation of the first galaxies. Numerous globular clusters of related stars are mixed in with the stars, and both the stars and the clusters orbit the nucleus almost radially. Our galaxy is surrounded by a huge hot gas halo that is several 100,000 light-years in diameter. A halo is a spherical cloud of stars surrounding a galaxy. The mass of the halo is thought to be roughly equal to the total mass of all the Milky Way's stars. Astronomers have proposed that the Milky Way's halo is composed of 2 populations of stars. The Paranal Observatory's findings indicate that the stars in the inner halo are 11.5 billion years old. The outer halo is thought to be made up of the stellar components of smaller galactic systems. The stars in the halo are older and have lower metal content than the majority of the stars in the Milky Way's disk. The halo also contains gas and dark matter. The halo is evidence of the 2 galaxies that collided billions of years ago and reinforces the idea that the Milky Way has a dynamic origin story. In the Milky Way's stellar halo, astronomers have also found more than 200 far-off variable stars referred to as RR Lyrae stars. These stars serve as important standard candles used to measure astronomical distances and are often found in globular clusters. The farthest star from Earth is about 1 million light-years away, nearly half the distance to Andromeda. About 90% of the matter in our galaxy is dark matter, or matter that is invisible to the human eye. Stars make up the remaining 10 to 15% of the visible stuff in the Milky Way, composed primarily of gas and dust. Simulations of the Milky Way's rotation have shown that this massive amount of dark matter produces an invisible halo. If the dark matter did not exist, then the stars within the Milky Way would orbit much slower than has been observed. The Milky Way's dusty ring can be observed in the night sky on a clear night. As we are located approximately 26,000 light-years away from the center of the Milky Way, we are unable to capture images of the disk from the outside. Any depiction of our galaxy that you have ever seen is either an artist's portrayal of it or a separate spiral galaxy. We don't have a picture of the Milky Way as a whole since we can only capture images of it from within the galaxy. So, why do we believe that it is a barred spiral galaxy? There are several clues. The first clue to the shape of the Milky Way comes from the bright band of stars that stretches across the sky in locations with dark night skies. This band of stars can be viewed with the naked eye. That band comes from seeing the disk of stars that forms the Milky Way from inside the disk and tells us that our galaxy is basically flat. Many telescopes, both on Earth and in space, have captured photographs of the Milky Way disk by capturing a sequence of images in different directions, similar to creating a panoramic photo with your phone or camera. The concentration of stars in a band adds to the evidence that the Milky Way is a spiral galaxy. If we lived in an elliptical galaxy, we would see the stars of our galaxy spread out all around the sky, not in a single band. The Milky Way galaxy was believed to be only a few thousand light-years large until around a century ago, and most people believed it to be the whole universe. Although other galaxies had been found, it was believed that they were only tiny objects inside our galaxy. French astronomer Charles Messier discovered the first galaxies in the 17th century, although he had no idea what they were at that time. As a skilled comet observer, Messier saw several additional fuzzy objects in the sky that he was certain were not comets. Fearing that other comet hunters would be misidentified as well, he put together a list to help them out. On Messier's list, 110 star clusters and spiral nebulae were detected. The objects are denoted by M for Messier, followed by a number, for example, M51. However, it took astronomers nearly 300 years to figure out what these fuzzy spiral nebulae were. Some claim that these nebulae were island universes, objects similar to the Milky Way Galaxy but existing outside of it. Others disagreed, thinking that these spiral objects were actually Milky Way gas clouds. The dispute continued until the 1920s when American astronomer Edwin Hubble measured the precise distance to a spiral nebula. Hubble discovered that one of the objects he was seeing was actually a Cepheid variable star in 1923 while studying the Andromeda Nebula, which is now known as the Andromeda Galaxy. First identified in the early 1900s by American astronomer Henrietta Leavitt, Cepheid variables are stars whose brightness changes periodically over time. Leavitt discovered a connection between a Cepheid's luminosity, or brightness, and its period, which is now known as the period luminosity (PL) relationship. The PL relationship can be used to calculate the actual brightness of a Cepheid by measuring its period, obtained by observing changes in brightness over days or weeks. Hubble established that the Cepheid he was studying in M31 was located outside our own galaxy by calculating its distance using the PL relationship. This put an end to the controversy surrounding the spiral nebulae and proved that they were, in fact, far-off galaxies similar to the Milky Way. Hubble continued his study of galaxy distances using Cepheids as his measuring tool before publishing his results in 1929. In his work, Hubble created a graph showing the distances to Cepheid variables and the velocities of galaxies, obtained by estimating the redshift of these galaxies' spectra. According to this graph, most galaxies are moving away from us, or receding, and their rate of motion, the recessional velocity, is inversely correlated with their distance from us. Distant galaxies recede more quickly than nearer ones. This was later known as Hubble's law. Hubble's initial estimates for the recessional velocity of galaxies were very high because, at the time, no one knew that there were actually several different types of Cepheid variables with slightly different period luminosity relationships. But as astronomy has advanced, the value of the graph's slope, known as Hubble's constant, has been reduced, and the results are now converging toward an accepted value of about 65 km per second per megaparsec. That means galaxies recede by an additional 65 km per second for every megaparsec they are away from us. There are trillions of galaxies in the universe, and up to a few hundred billion stars can be found in each galaxy. Just as one studies atoms to understand the qualities of a material, one must study the building blocks of the universe to comprehend it. Understanding the formation and evolution of galaxies is essential for our understanding of the universe. Although the study of galaxy formation dates back around 50 years to the foundational work of Egan, Lynden-Bell, and Sandage, we still do not have a comprehensive understanding of how galaxies form and evolve. Many details still need to be explored. In addition to providing valuable answers to questions like, where do we come from, and where are we going, observing other galaxies enables us to draw several conclusions about the evolution of the universe. The only galaxy we have access to a vast amount of data on is our own. The other galaxies are just too far away for us to observe star by star. One might wonder if knowledge of the Milky Way's development provides any insight into other galaxies. The answer is yes. Approximately 50% of stars in the modern universe reside in Milky Way-like galaxies. To put it another way, the Milky Way is a fair representation of a typical galaxy in the universe. Our knowledge of the Milky Way's development will provide a strong foundation for understanding other galaxies. Soon after the Big Bang, which occurred 13.8 billion years ago, the Milky Way began as one or more small overdensities in the universe's mass distribution. Some of these overdensities were the seeds of globular clusters in which the oldest remaining stars in what is now the Milky Way formed. It's possible that about half of the material in the Milky Way originated in other far-off galaxies. These star groups and individual stars now make up the Milky Way's stellar halo. The Milky Way's mass reached a point where it began to rotate relatively quickly only billions of years after the first stars were born. Because of the conservation of angular momentum, this caused the gaseous interstellar medium to compress into a disk from a roughly spheroidal shape. Therefore, later generations of stars formed in this spiral disk. Throughout its history, the Milky Way has consumed many galaxies to get to its current size and form. In the last 12 billion years, the Milky Way has swallowed up more than a dozen galaxies, according to cosmological simulations. It merged with a particularly massive galaxy known as the Kraken approximately 11 billion years ago. Our galaxy is currently consuming the Canis Major Dwarf Galaxy by adding the smaller galaxy's stars to its own spiral. At present, the Milky Way is traveling at a speed of 250,000 miles per hour in the direction of the Andromeda Galaxy. It is expected that the two galaxies will collide in roughly 4.5 billion years. The Milky Way and Andromeda are the two largest galaxies in the local group, and they will merge because, before dark energy took over, they became gravitationally bound to one another. The merger is expected to change the night sky over Earth. The Milky Way is orbiting a point in space that is roughly halfway between it and the Andromeda Galaxy. Although it's difficult to believe, experts think that our solar system will probably survive such a terrible event. Since galaxies are primarily made of empty space, this collision will not have a significant impact on our solar system. Despite having 100 billion stars each, our galaxy and the Andromeda Galaxy are very far apart. Currently, Andromeda is located 2.5 million light-years away from Earth. Similar to how a ball in the air accelerates faster as it falls toward Earth, Andromeda will be drawn closer and faster by the Milky Way's increasing gravitational pull as it gets closer. In just 4 billion years, the Milky Way and Andromeda will have tugged and ripped at one another's throats. All that's left will be the spectral framework of two separate galaxies. The carnage will go on for as long as time does not stop until the central supermassive black holes in both galaxies are near enough to one another to collide and join. By that point, the Milky Way and Andromeda galaxies, two separate spiral galaxies, will be no more. Our solar system will have a new home in an entirely different class of galaxy called an elliptical galaxy. What about life on Earth then? Will life on Earth continue after the merger? Well, in roughly 7.5 billion years, the Sun will grow larger and swallow the Earth, turning it into a red giant. Ultimately, in a timeline of about 4 billion years, as solar radiation reaching the Earth increases, Earth's surface temperature will increase. We might experience a runaway greenhouse effect much like what's happening right now on Venus. Thus, there's a good chance that life on Earth won't exist after the merger. However, perhaps by then, some people on Earth will have developed space travel abilities. It's possible that we will have abandoned Earth and our solar system. The view of Andromeda colliding with the Milky Way might still be available to us, although from a slightly different angle. As we gaze up at the night sky, let's realize how short our life is. We are stardust, seeing a cosmic tale unfold. For whatever reason, we are here now, sitting and wondering about the universe. We, the very children of the universe, born from ordinary chemicals over billions of years, now gaze wondrously into the endless black abyss. To think about it, we are just a tiny speck in this grand cosmos, and yet, our curiosity drives us to explore and understand more. The Milky Way, with its spiral arms, stars, and mysteries, is a vast and beautiful entity. Our journey today has taken us from our familiar solar system to distant stars and unimaginable phenomena. From the protective heliosphere and the edges of our solar system to the enigmatic black hole at our galaxy's core, we have seen the intricate dance of celestial bodies that make up our galactic home. Our solar system's position in the Orion Arm, the colossal size of stars like Uy Scuti, and the dark, mysterious nature of Sagittarius A** remind us of the scale and complexity of our universe. Each discovery and every piece of knowledge builds a more comprehensive picture of where we are and where we come from. As we continue to explore, we learn more about the galaxies beyond our own. We understand that the universe is expanding, filled with countless galaxies each with their own stories. Our own Milky Way's future, with its eventual collision with Andromeda, paints a picture of constant change and evolution on a cosmic scale. while we may never see the full journey of our galaxy, our pursuit of knowledge brings us closer to understanding the universe's grand narrative. The stars we see tonight are the same ones that have inspired humans for centuries and will continue to do so for generations to come. So, as you look up at the night sky, remember that you are a part of this incredible cosmic journey. The stars, planets, and galaxies are not just distant objects, they are part of our story, our heritage as beings of the universe. Embrace the wonder, continue to question, and keep exploring. The universe is vast, and our journey through it has only just begun.